for the next session of the today's workshop. So the next talk by Professor Basil Birende. So he will speak on first one or this one only?
This one.
Same.
Now is this one, but this was intermediate.
Okay. So he will speak on applied fixed points, interior self-adaptive algorithms solving split feasibility problems. Okay. So he will discuss, interact, and talk in this title. Please, Professor.
So the main goal of this second part is to show concretely how we can apply the ideas in this introductory part related to iterative fixed point iterative methods for non-expensive time mappings. But before I go into this presentation, I want to just show you a few aspects about the problems I mentioned here. No, this is not good. It's better to do this. So I just want to recommend you to read this paper. When I'll put here, you can send to all participants.
Yeah, I will send to this evening.
This is what I presented for short, and here are these definitions. Sorry, why you don't work? Here is the whole content of what I presented, including these examples treated in great detail, and the diagram I mentioned is here between these four important classes of non-expansive type mappings. And the detailed proof. So many things you can find here. And I encourage you, if you are interested, to have a look on this. Now we should go to this one, which is the topic for today. So I would like to present a concrete application of these fixed point iterative schemes to solving a general problem in our area, the so-called split feasibility problem. Split feasibility problem, it's a very large set of problems that we incorporate here. Many problems are can be defined as a split feasibility problem. So why to deal with this kind of problems? You have here some arguments. This general class of problems includes a lot of important problems in nonlinear analysis, which are modeling various inverse problems. You know about image reconstruction problem or X-ray tomography. You know about signal processing. Medical care is this intensity modulation, modulated radiation therapy, statistical learning, and many others that I do not mention here. So under the umbrella of a split feasibility problem, we actually can find a lot of usual common problem, like fixing point problem, common fixing point problem, and so on. In my opinion, the most important kind of problems in that area are these inverse problems, which are not artificial problems, but they are coming directly from the real world application. So we need to consider such kind of insert problem. You can have a look on what I extracted here from 4 important databases. So in Scopus, you will find this number of articles containing these 3 words split feasibility problem in the title. Not all papers dealing with a topic include this topic in the title, but if you can imagine that if you search in Scopus for papers containing split feasibility problem in the topic, we'll have 3 times more papers. But I selected just this one. In MathSciNet is this number of papers. These are reviewed here in MathSciNet. You should know that some journals which are indexed in Scopus are not indexed in MathSciNet. So this is the explanation for the a few numbers is the difference. In Web of Science, so ESCI, there is this number of papers containing this split feasibility problem term in the title, and in Central Blood Math, which is the oldest database in mathematics, we have this bigger number of papers reviewed. Just to mention an interesting fact, this Central Blood something was founded in this year in Germany. They started to review mathematics papers. Maybe you are not using MathSciNet, Central Blood Math very often, but I do recommend. In these databases we found, if you are interested in a certain topic, then you will find, for example, by searching with keywords, we can find what we are interested. It is not the topic of these presentations, but I'll speak in KingFab next week, actually after 2 weeks, not next week, but the other one. I'll speak about B-metric in several fields of applications, and there I'll show how I discovered the first paper ever published related to B-metric spaces in Central Blood. It was not possible to find it by keywords, by anything, because the title was different, was topological title, and so I insist. These 2 mathematics databases, MathSciNet and Central Blood Math, are very useful. And what is interesting, the new database in Central Blood, this is the German name. So Central Blood, it's the name, it's a journal, it's a name in German. This was the new version was founded in 1930 by Neugebauer, a German mathematician. And MathSciNet was founded in 1940 or 1939 by the same. He moved to USA because at that time in Germany there were some issues. And
AMS.
yes, AMS, so mathematical reviews.
American Mathematical Reviews.
Yes, mathematical reviews under this name. He found it both the best.
By the same person.
Yeah, by the same person, Neugebauer, very great mathematician and a specialist in history.
Before the Second World War.
Yes, before the second, because he moved in Germany in this period, 1930, 1933. There were starting problems with Jewish people. They have to emigrate.
We don't find papers between those. That
Yeah.
because of World
So these are great. So use this. This is my suggestion. When you are documenting on the topic, use these databases. These are the best one. This is free, totally free. This is not completely free, but you can find it displays only 3 results of the. But I don't know. The Americans should take the German model and it will be fully open.
That is not free at all.
Yes, this is not free, but
You want to search, then you need to pay some $12.
yes. We have in Romania we are paying.
We subscribed here.
So we have
Math science.
full access to all these databases based on a subscription. So
Direct also.
subscription is not cheap. It's very expensive, but we have in Romania all university are forming a kind of organization, and through this organization we have subscriptions to all these databases, and we have full access to most of them, including Elsevier publications, Springer journals, all these main publishers in
We
mathematics.
have database in our country by Government of India, but mathematics is very poor.
Okay, it's a
Things are fine.
So, to conclude this motivation, split feasibility problem consists in very many typical problems related to our field. So, it is immediately a fixed point problem, can be written as a fixed point problem, and we should use such kind of iterative. I forgot here to put one important algorithm. I knew I included it, but this is
Hong Kong Zoo.
no Halpern iteration, which is very important because it ensures strong convergence in many instances where we don't have strong convergence for these 3. And the specificity of this one is the following one. This is defined, let's say, in this form. No xn, but u and lambda n t of xn, and u is called an anchor. Anchor, it's this term. We anchor the iteration on this fixed point, and it's a fixed point taken from the beginning, and this iteration has the property that we get a strong convergence. This was improved by replacing this anchor by contraction map. Very nice idea, are called the same viscosity type by a French mathematician, but is not the scope of this presentation. So we can use, because a split feasibility problem can be converted naturally in a fixed point problem, we can apply these algorithms, and this is the way we are doing. The problem itself is defined in this way. We have a Hilbert space H1, and C is a closed convex subset of it. We have a second Hilbert space H2. They can be the same, no problem. And Q is again closed convex. And we also have a bounded linear operator A that maps H1 to H2. So, by definition, the split feasibility problem is asking to find a point in the first set, C, such that its image by the linear bounded operator is in Q. So this is the problem. If we have a close look, we can see that if the spaces coincides and if the set also coincide, this is actually a kind of inclusion problem. Inclusion problems are contained by split feasibility problem, but many others. It is known, and I refer to this nice paper by Byrne. I wrote a letter recently to Byrne about, I don't remember, maybe I invited him to review a paper, and he said, oh no, I'm now retired for many years, he should be more than 80 something, and he said, I'm not more interested in this kind of problems, split feasibility problems, to review. So it is known that such a problem, look how it is stated, is actually a fixed point problem. And what is here? This x which satisfies this problem is the solution of the fixed point of this operator T. But look, here we have two elements. P, C, and PQ are the metric projections. We should be familiar with the metric projection. In a Banach space or in a linear space, we project orthogonally an element outside the set C on C and respectively on Q. So I is the identity map and A star is the adjoint of the operator, linear bounded operator A. So with this tool, any split feasibility problem, it's a fixed point problem. Okay, then it is clear that we immediately can construct an iterative scheme, just considering Picard iteration. Picard iteration is, this is our operator T, so xn plus 1 equal T of xn. And it is known that this is a very important algorithm in solving split feasibility problem, but also fixed point problems for non-expansive mappings. It is called CQ, because one set is C and the other set is Q. So this was the way the authors introduced this terminology for this algorithm. CQ algorithm. This is known that if we have some restriction of this parameter gamma, which is in this set, lambda is the spectral radius of the operator A star times A, then for sufficiently small values of gamma, we know that this operator is non-expansive. This is the key. So, look, we started from a problem where we have nothing about non-expansiveness. Nothing. It's just set closed convex is closed convex, but as I mentioned in the last slides at the previous presentation, the orthogonal projections is a non-expansive map. Actually is firmly non-expansive. So it results that this map we have here, this operator, is non-expansive. So at this moment we are in the family of our non-expansive time mappings, and we are done. So we know a lot of how to approximate non-expansive, a fixed point of non-expansive type mappings, so we can use a convergence theorem and resolve the problem, split feasibility problem. In many other contexts, for various problems, we have similar equivalences. I mean, a concrete problem is translated equivalently, is transformed equivalently into a fixed point problem. And now again, I refer to these mappings because I'll use for the following considerations and their relation, just to remind, because I'll solve a split feasibility problem which has been solved in this class, I'll solve in this larger class. This is the profit of what I said, the usefulness of the fact that the class of demi-contractive mappings is saturated. So, our starting point is this paper from 2019 by two Chinese mathematicians, a fixed point method for solving a split feasibility problem in Hilbert spaces. These authors solve our problem, number one, in the class of non-expansive mappings by using such an algorithm. Such an algorithm is not difficult to read. So we start from x1, arbitrary in the set C, then we construct, we have the linear bounded operator A given, we construct the projection operator Q, we construct this operator, then we project all on the set C, and then this is the here is T. Here should be T, because T is a non-expansive mappings with a fixed point set different of zero. Such an algorithm is called of viscosity type because here, and it's a Halpern time algorithm, here instead of the anchor U, this U we have a contraction. You can see that G is a Banach contraction, T is the central operator here is non-expansive with the set of fixed point non-empty, and alpha n, beta n, gamma n, delta n, and theta n are some sequences which are involved here in the construction of this algorithm. It should be important to note that we have some convex combination here, but I'll show you later. You can see that here we have 1 minus delta n xn, and we have delta n tn. Sorry for this. I have to remember to change this is t, because I changed somewhere this in t. So they prove that this sequence, which is generated in such a way, converges strongly to a fixed point of this map T, which is also a solution of the split feasibility problem, which we denote as if Fp of CQ, and this X star, this solution, is also the unique solution of a variational inequality. So, in total, we solve a fixed point problem, we solve a split feasibility problem, and we solve a variational inequality. So, three problems. Our solution is actually a solution of three different problems. Fixed point problem, split feasibility here, sorry, split feasibility problem, and variational inequality. Okay, these authors here in 2000, very recently, 22, they solved the same problem, but they weakened the condition of the parameters. Again, I have here alpha n 2 times. I don't know why, involved in the algorithm. They inserted an inertial term. I'll show you, I'll explain what is an inertial term. So inertial means the following fact. At a certain moment, we compute the iteration xn. And to have an inertial term means that we'll take an intermediate value, let's say yn, which is xn plus theta n, xn plus 1 minus xn. So this is what is called inertial. This is from physics, to keep the inertial character of the two iterations. So when theta n is 0, then we get a normal iteration. So this means inertial algorithm. So sorry, they did this by inserting this inertial term and succeeded to choose the step size. Step size is involved in the algorithm. Is not needed to be calculated. Usually we need to calculate the norm of this operator A, which is not a simple problem. And they extended the previous results to quasi-non-expensive mappings. I remind you that the previous study was devoted to non-expensive. So we should have in mind all the time this relation. So non-expensive is included in quasi-non-expensive. But they did in a different way, not in the way we should do by extending from quasi-non-expensive. And some other authors contribute to this subject. I mention here these two Thai mathematicians. They published the paper in 2020. It's a very recent paper, and also these authors, the first one is from Spain, and the second, this is Xu Ku. This is a very strong Chinese mathematician. He is a friend of mine. I visited him in China some 5, 6 years ago, I guess. He did extraordinary deep results into this field. And they improved this algorithm by not using the knowledge of the matrix norm. So these are the basics where we start our interest. So our interest was to extend these last results by Wang, Xu, and Yao and Jiang from quasi-non-expensive mappings to the more general class of, the formulation is correct. My interest was to see if we can extend from quasi-non-expensive to a larger class of mappings. And as we know, demi-contractive mappings are here, and I explain how I can transport a result from here to here. We propose a hybrid inertial self-adaptive algorithm, and we solve the problem in the class of demi-contractive mappings. So in this larger class. And due to this fact, The results I propose are very general. They are extending all previous results from passing from non-expensive mapping